Alright, so in this video lesson, we're going to go ahead and do a Unit 3 review for the test. Remember, the Unit 3 is topics 9 and 10. This review is going to be covering 12 questions that are very reflective of things that you will see on the exam in one way, shape, or form. Remember that even though this is a very good indicator of what you'll see on the exam, this is by no means an exhaustive review. So please make sure that you go through your review notes, make sure you go through practice problems we've done in class, as well as worksheets that I provided on Canvas and things like that, so that way you're prepared. But nevertheless, let's go ahead and get started. Alright, so let's go ahead and get started with just a simple balancing equation problem. So you'll notice here that this is a double replacement reaction, and a lot of times in double replacement reactions you have polyatomic ions. And so what happens is when you have polyatomic ions like phosphate here or nitrate, if they're located on both sides of the arrow, such as they are over here, phosphate and nitrate, go ahead and just keep those together. So what I'm going to do is I'm going to start off by just drawing a line under the arrow, so that divides the reactant and the product side. Now I'm going to go ahead and list all my elements that I have, and when I get to a polyatomic ion, I'm going to go ahead and just keep that together. So I have sodium, I have phosphate, so I'm going to keep that together, PO4, I have lead, and then I have nitrate. Okay, and I'm going to actually write it in the same order on the product side. There we go. Now the next thing you're going to want to do is you're going to want to go ahead and write the numbers of each of those things that you have on the reactant and the product side. So starting on the reactant side, I have 3 sodiums. Now be careful, you might be tempted to say you have 4 phosphates, but remember the 4 is how many oxygens you have. Phosphate actually is PO4, and so you only have 1 of them. Lead you have 1, and then nitrate you have 4, because notice you have the 4 on the outside. On the product side, sodium's over here, we have 1 of them. Phosphates we have 4. Leads we have 3. And then nitrates we have 1. Once again, don't be tempted to put 3 just because it has a 3 here. Nitrate actually is NO3, and you only have 1 of them. Now this, if you notice with the numbers that we have written down, you'll notice that we don't have nice easy numbers such that, like, you know, they're all 1s and 2s. If they're 1s and 2s, that's easy because all you have to do is just double 1 and then you're good to go. But in this case, you've got 3s and 4s. And 3s and 4s don't really have an easy multiple, just like 3s and 2s don't, remember? So when you have a situation like that, you want to look for the least common multiple. And so what is the least common multiple for 4 and 3? And the answer is 12. 4 times 3 is 12. So keep that in mind. 12 is going to be the number that we are kind of hitting in case we get into a snag. So here's what I mean by that. So let's say we wanted to start out by balancing our sodiums. The product side is the deficient side. So I want it to be 3, right, to match the 3 that's over here. So then over here, I'm going to say, all right, sodium, where's sodium? Sodium's right here. And so what number could I put in front of here to make the sodiums 3? And obviously that is 3. So that's going to change my sodium to 3. And it's also going to change my nitrates to 3. Now here's the problem. Okay, your nitrates are 3 on this side, and they're 4 on this side. That's where you get into that problem where there's nothing you can do to just one side to make it balance. You're going to have to do something to both sides. And so actually, this is where your least common multiple comes into play. So I'm actually going to go back to what I just did. Instead of putting a 3 right here, I'm going to actually change that. I'm going to go ahead and put a 12 there because 12 is my least common multiple. There we go. So by putting a 12 there, my sodiums actually are 12 and my nitrates are 12. So now on the reactant side, I'm going to go ahead and make these numbers for sodium and nitrate equal to 12 as well. So right now I have 3 sodiums. Okay, I want to make that 12. So by putting a 4 here, that's going to actually change my number of sodiums to 12. And so now those are balanced. For nitrates as well, nitrate is right here. Okay, if I put a 3 there, that's going to change my nitrates to 12. And so now sodiums and nitrates are equal out. Well, let's go ahead and see how that changed the other ones. Phosphate, okay, phosphate's right here. 4 times 1, that makes this 4. And if you notice, that actually balances out with what's on the product side. For lead, if by putting a 3 here, that makes lead equal to 3 on the reactant side. And that makes it equal also on the product side. So by noticing that least common multiple of 12, I was actually able to save myself a lot of time and effort by just knowing that that was going to happen. So the balanced equation would be 4, 3, 1, and 12. All right, let's go to question 2. Okay, so question 2. Let's actually get rid of this work right here because that was the last problem. There we go. All right, so question 2. Question 2 now is taking a look at your types of electrolytes. The question is, circle all of the following that would be considered strong electrolytes. So remember, there are 3 types of solutes. There's a strong electrolyte, and that means they're going to ionize completely. There's a weak electrolyte, which means only partial ionization. And then non-electrolytes. And non-electrolytes don't produce any ions in solution. So this question is specifically asking for what are strong electrolytes? Well, there are 2 things that you will look for to see if something is a strong electrolyte. The first thing you'll look for is an ionic compound that is dissolved in water. So let's actually stop right there. Looking at the 3 compounds that are listed on the screen, let's find the 3 ionic compounds that are there, because there's 3 of them. This is an ionic compound, this is an ionic compound, and this is an ionic compound. So those are the 3 ionic compounds that are there. So those are 3 potential strong electrolytes. But there's one thing we have to check for. We have to actually see if they dissolve in water. Because if they don't dissolve in water, they're not going to be electrolytes because they're not going to produce ions. So taking a look at the very first electrolyte possibility, calcium sulfate, we take a look at our solubility rules, which are on the back of your periodic table. If you look at those rules, rule number 4 has to deal with sulfates. Any compound that contains a sulfate ion would most likely be aqueous. It would most likely be soluble in water. But there are some exceptions, and one of those exceptions is when sulfate is bonded to a calcium cation. If sulfate is bonded to calcium, it actually is not going to dissolve in water. So even though calcium sulfate is an ionic compound, it's not soluble in water, and therefore it can't ionize. So it's not going to be a strong electrolyte. Now the next ionic compound, potassium chloride, that contains a group 1A ion because potassium is found in group 1. And if you recall, any ionic compound that contains a group 1A ion will dissolve in water. So because it dissolves in water, potassium chloride is going to be a strong electrolyte. The last ionic compound is lithium bromide, and for the same reason as calcium chloride, lithium bromide is also going to be a strong electrolyte because lithium is a group 1A ion, and therefore that's going to dissolve in water. So far we've identified 2 ionic compounds that are going to be dissolved in water, and therefore 2 strong electrolytes. But strong electrolytes are not just soluble ionic compounds. The other thing that can be a strong electrolyte is if it is one of the 7 strong acids. So take a look to see, first of all, are there any acids? And there are. It's HNO3. Is HNO3 one of the 7 strong acids? Yes, it is. And so since it is one of the 7, HNO3 is also a strong electrolyte. The other 2 that are here are actually molecular compounds, and so those actually would be non-electrolytes, so they definitely are not going to be strong. Okay, so to review, a strong electrolyte is either going to be a dissolvable in water ionic compound, meaning it's going to be aqueous, or it's one of the 7 strong acids. That's how you will know it is a strong electrolyte. All right, moving on to question 3. Okay, whoop. All right, so question 3. This actually is not topic 9 or 10. It actually technically is topic 2. It's a simple conversion question. So the question is asking how many atoms are there in 0.4972 grams of iron 3 chloride. Okay, so this actually, like I said, it's not a topic 9 or a topic 10 question per se. It's more of a review. So you're starting out with something in grams. Okay, so we are currently in grams, and it's asking for how many atoms. Okay, and so we are trying to get to atoms. All right, well, there's not a direct conversion to get from atoms or from grams to atoms, but what we can first do is we can go from grams to moles. Alright, once you are in moles, you can get to anything. Now, we're trying to get to atoms, which atoms is a particle. Anytime you are trying to get from moles to a particle, you're going to use Avogadro's number. But be careful, with Avogadro's number, it's always 6.022 times 10 to the 23rd of whatever it is that you have. So you have to take a look at what is it that we're looking at. We're looking at iron 3 chloride, and iron 3 chloride is a compound. It's not an atom. So when we use Avogadro's number for moles, we're actually not to atoms yet. We actually just get to molecules, or more specifically, we get to formula units. A formula unit is just an ionic compound. Once you're in formula units, you will then be able to go to atoms, and I'll show you how to do that in the conversion setup. Okay, so let's go ahead and set this up now that we know kind of our roadmap that we're going to do. So we are currently in 0.4972 grams. All right. So my first conversion is to get me from grams to moles. All right, and so we're going to do this by doing molar mass. So we need to first know what is the formula for iron 3 chloride. This is another thing that will be difficult for students, because if you can't write the formula correctly, then you're not going to get the molar mass correct. So iron is Fe. It has a positive 3 charge. That's what that Roman numeral 3 means. Chloride comes from chlorine. Chlorine's -1. So to balance those charges out, you actually need 3 chlorines in order for this to balance out. And so we need to figure out what is the molar mass for FeCl3. So iron is 55.85, and then 1 chlorine is 35.45. So we need to multiply that by 3 in order to get our molar mass. And so the total molar mass for this compound, for every 1 mole, it's going to have a molar mass of approximately 162.2 grams. Let me make sure that point's there. There we go. Okay, so that's going to get rid of grams, and now we are in moles. So the next thing we're going to do is we're going to get from moles into particles. And the particles specifically we're in, since it's a compound, is going to be formula units. And remember, formula unit is just, it's an ionic molecule, if you want to think about it that way. So if it makes you feel better to write molecules, even though that technically is not correct, for the math, it's fine. Okay, so moles will go on the bottom. That way it'll cancel out. And we're going to put formula units on top. So I'm just going to abbreviate F dot U dot. All right, 1 mole of anything is going to contain 6.022 times 10 to the 23rd of that thing. So moles will cancel out, and now we are in formula units of this compound, the FeCl3. So now the last thing is, for every 1 formula unit of FeCl3, how many atoms are in 1 formula unit? So think about it. For every 1 molecule of iron 3 chloride, 1 molecule of FeCl3, how many atoms? The answer is you have 4. You have 4 atoms. One of those atoms is the iron, and the other 3 are the chlorine. So total, there are 4 atoms. That right there is the last conversion you have to do in order to solve the problem of how many atoms. So now we're going to go ahead and calculate that through. So 0.4972 times Avogadro's number, 6.022 times 10 to the 23rd, times 4, and then divided by the molar mass of 162.2. We end up getting, hold on, my calculator did something weird. There we go. We end up getting the number of atoms is going to be, with correct sig figs, is going to be 7.384 times 10 to the 21st atoms. Alright, so that's how many total atoms would be in that mass of iron 3 chloride. Alright, okay, let's go ahead and move on to question 4. So, apologize, we got to get rid of that writing. There we go. Okay, so now question 4 asks us to write the complete molecular, ionic, and net ionic equations for the reaction between magnesium nitrate and potassium sulfide. Include phases with each substance and balance each equation. So the molecular equation, remember, is just the chemical equation. So I already know what my reactants are. Okay, they are magnesium nitrate. Okay, so let me write this down. And that's going to be aqueous, because remember, you always have a double replacement reaction between two aqueous reactants. So that's the first reactant. Plus the second reactant is K2S, and that's also aqueous. Alright, so now we have to predict the products. So remember, in a double replacement reaction, the cations are going to switch. So the magnesium and the potassium are going to switch spots. So the magnesium is going to end up bonding to the sulfur. Notice I don't write any subscripts yet, because I need to see what needs to happen now that they're bonded to new elements. Magnesium is +2, sulfur is -2, so it's actually okay to just write Mg and S. Now I need to predict what that state of matter is going to be. I'll do that in 1 second. Let's go ahead and write the other product. So the potassium will bond to the nitrate, so KNO3. The only subscript I bring over is the 3, because that's part of what nitrate is. Okay, so potassium's +1, nitrate's -1, so that is the correct way to write that. Once again, I'll need to know what the state of matter is. Alright, so the easy one is to write the state of matter for the second one. And the reason why that's easy is because, remember, anytime you have a compound that has a group 1A ion, it's automatically going to be aqueous. Potassium is it's group 1A, so it's aqueous. However, the one I do need to check is magnesium sulfide. That could be aqueous as well, in which case there's no reaction, or it could create a precipitate. So I'm taking a look at my solubility rules right now, and I'm looking for the rule that has sulfide, not sulfate, but sulfide. And that's going to be rule number 6. So rule number 6 states that sulfide ions that are in compounds generally are insoluble, meaning they're generally solids, unless they're bonded to, and then it lists some exceptions, but magnesium is not one of the exceptions. So since there's no exceptions, that actually means this is my solid, and that's my precipitate. The last thing I need to do is I just need to make sure I balance this. What I need to do is I need to put a 2 right in front of there. Alright, so that's going to balance my chemical equation there. So now the ionic equation is going to go ahead and break everything up into ions. So what I'm going to do is I'm just going to get you started, and then I'll go ahead and just kind of reveal everything, because you don't need to see me watch me do everything. But remember, there's 3 things you want to watch out for whenever you are writing out your ionic equation. You want to make sure, 1, you have the correct quantity, 2, you have the correct charge, 3, you have the correct state of matter. So an ionic equation is breaking up everything that's aqueous. So let's go through our first reactant here. Let me choose a different color. I'm going to choose green, just so we can make this look different. Okay, so my reactant right here is aqueous, so I need to break all that up. My first ion is the magnesium ion. So I have 1 magnesium, so I'm just going to write Mg. The charge of magnesium is +2, and it is aqueous. Plus, the second ion is nitrate. Okay, how many do you have? I have 2 of them, so I'm going to write it as a coefficient. So I have 2 of them. Nitrate has a -1 charge, and then last thing is, what's the state of matter? AQ. Alright, plus, then I get to my second reactant here. It's also aqueous, so I break it up. My first ion is potassium, so how many do you have? 2. Potassium's charge is +1, and it is aqueous. The second ion there is the sulfide ion. There's 1 of them, so I'm just going to write S. Sulfur has a -2 charge, and it is aqueous. The biggest mistake students make with these is they either forget the phase of matter, or they forget the charges. So just make sure you're always asking yourself those 3 questions. How many? What's the charge? What's the state of matter? On the product side, we have MgS. Okay, that's solid, so we're not going to break that up. We're going to keep that together. MgS. And that I'm going to keep that state of matter solid. Plus, okay, over here, we end up having our potassium and our nitrates. It's aqueous, so we need to break that up. That coefficient 2 is going to apply. So there's 2 potassiums, +1 charge for potassium, and it is aqueous. Plus, there's also 2 nitrates. Okay, so nitrate has a -1 charge, and it is aqueous. Now, you'll notice in the ionic compound, or the ionic equation, that there's actually 2 ions that don't do anything in the reaction. And those 2 ions are the potassium ion and the nitrate ion. Okay, so right here, nitrate and potassium, they're also on this side as well. So remember, we call those spectator ions because they don't do anything. If you wanted a really quick way to find out what the spectator ions were, remember, all you have to do is come up to the molecular equation and look at the product side. Anything that is aqueous still on the product side, those two ions are going to be spectator. So the net ionic equation removes those spectator ions. So the only difference between the ionic and the net ionic is we're just removing the spectator ions. So the net ionic, I'm going to go ahead and write out my Mg, 2 plus aqueous. I'm not going to include nitrates, I'm not going to include potassiums, but I'm going to bring down the sulfide. Okay, so I'm just bringing that down. And then what do they make? They make the precipitate. If this reaction did not actually make a precipitate, there would be no net ionic equation. So in other words, if both of your products were aqueous, you would still have a molecular equation, you would still have an ionic equation, but you wouldn't have a net ionic equation because you're not making anything. You have to have a solid or a liquid as one of your products in order for there to be a net ionic equation. So that is how you write a molecular, an ionic, and a net ionic equation. Okay, so we're going to look at the same problem that we were dealing with. So it says, assuming that K2S was the limiting reactant in the previous problem, draw what the resulting beaker would look like after mixing. So let me put on the screen real quick to remind us what the molecular equation was. Okay, so regardless of anything limiting, regardless of anything excess, if you have a reaction between these two reactants, you are definitely going to at least have those two products. So the solid magnesium sulfide and the aqueous potassium nitrate, those two products are going to be there regardless of limiting or excess. So the first thing you want to do, if I ask you to do a beaker drawing, is just draw those two products. So I'm going to draw the solid at the very bottom because that's your precipitate, that's clump. So MgS, and that's how we draw it. We just do like a little clump at the bottom. For the second product, the 2KNO3, that's aqueous. So I'm going to draw that as they're floating up here in ion form because that's what they are. So there's 2 potassium ions and there are 2 nitrate ions. So this right here is just your 2 products. So this right here down was product number 1. And this right here was product number 2. Additionally, you need to also draw the excess reactant because if you have a limiting reactant, if you have a reactant that got used up all the way, the other reactant, there must be some left over that was never reacted. So this problem is saying, assume that K2S was the limiting reactant. So we are assuming this reactant ran out. And so then by default, what reactant then has left over? It's this reactant right here, the magnesium nitrate. So we need to draw the magnesium nitrate in that beaker as well to show that that is the excess reactant. Okay, so I'm going to do it in red just so you can see that this is the, additional. So in addition to these 2 products we've already drawn, I'm going to draw in 1 magnesium ion. Okay, so that's a 2 plus charge. And then I'm going to draw 2 additional nitrates, NO3, because that's what's right here. If you didn't want to split those up, 2 nitrates there and 2 nitrates there, but you just wanted to write 4 nitrates total, that's totally fine. I don't care. But I'm doing it this way just so you can see that this right here is the excess reactant. I have to draw that in there. Okay, so this magnesium, just so you know, kind of have an idea of what's going on here, this magnesium right here wants to create more precipitate. It wants to create more magnesium sulfide, but can it? No, because there's no sulfide ions here for it to bond with. If you added more K2S to the beaker, then the reaction would continue. But right now, this excess reactant is just sitting here waiting for more of the limiting reactant to show up. So that's how you would draw the beaker if I asked you to do that with the products as well as the limiting reactant is K2S. Okay, question 6 is like the mother lode. This is probably, it's one of the questions that's worth the most points on the exam. Now, by no means put all your effort into studying this and then don't study anything else, but I definitely just want you to be aware that this type of question is it's going to be worth a lot of points. That being said, you also get a lot of points for partial credit. So if let's say you just didn't know how to do this, you got nervous, whatever, at least try to do as much as you can, because you can get partial points for at least doing correct setups and things like that. So the question is asking, determine the physical states of the products below and balance the equation. Then calculate the theoretical mass of precipitate formed if 0.4820 grams of sodium hydroxide are reacted with 52.81 milliliters of 0.3189 molar iron 2 chlorate. Okay, a lot of stuff there. Let's just break it down, okay? First things first, no matter what, if you don't know what to do, you start out with a balanced chemical equation. So we have the equation written out, we just have to balance it. Okay, so taking a look here, it looks like I don't have any crazy subscripts, okay? So my subscripts are 1s and 2s. So that's nice. I don't have to worry about that least common multiple situation. So I'm just taking a look at both sides. It looks like I've got actually, let's start over here. I've got one iron, 2 chlorates here. I've got 1 chlorate here. So I'm going to go ahead and put a 2 right there. That changes my sodiums to 2. I've got 1 sodium here, so I need to put a 2 there. And then 2 hydroxides, 2 hydroxides. So there we go. 1, 2, 1, 2 is going to balance that out. I also need to determine the physical states of the product. So it's leaving it blank here. It's asking us to use solubility rules to figure out what those states would be. I already know this second product is going to be aqueous because of the sodium. But this one right here, iron 2 hydroxide, I'm going to take a guess it's a solid, but you don't know. Okay, you got to check. So I'm looking for the rule for solubility for hydroxide. And that looks like it's rule number 7. Hydroxides are generally insoluble unless they're bonded to any of the exceptions. And iron 2 plus is not one of the exceptions. So that means that that's going to be a solid. Okay, so right there you've earned probably like 3 points right there, just being able to balance and predict the product phases of matter. So we're off to a good start. So now it's saying calculate the theoretical mass of precipitate. So which one am I going to be solving for? I'm going to be solving for the iron 2 hydroxide, this one right here. Okay, because that's the precipitate. So I don't care about this second product. I care only about this one right here. Let's write the information that I have down. So for the sodium hydroxide, I actually have the mass. It's 0.4820. And then for the iron 2 chlorate, since that's an aqueous solution, I have a volume of that. It's 52.81 milliliters. And its molarity is 0.3189. All right, so this is a classic stoichiometry problem. So what we need to do is we need to do the 3 mathematical steps of stoichiometry, and we need to do them for both reactants because we don't know which reactant runs out first. So we're going to have to do the process twice. So let's start out with the very first reactant. I'm going to go through the 3 stoichiometry steps for my very first reactant, the iron 2 chlorate. Okay, so step number 1 is take what you're given, convert it to moles. So hopefully by now you are very comfortable with being able to do this for an aqueous solution. So I'm going to start out with my volume of 52.81 milliliters. First thing I need to do is I have to convert that into liters. So there are 1,000 milliliters for every 1 liter. Okay, so that's going to make my milliliters cancel out. All right, my next step is now that I'm in liters, I can use the molarity. For every 1 liter of solution, it's going to contain 0.3189 moles of that particular substance, which is the iron 2 chlorate. All right, so my liters cancels out, and now I'm in moles. All right, so this was step 1 right here. I converted to moles. Step 2 of stoichiometry is use a mole ratio to convert from the compound you're currently in to the compound you would like to solve for. So currently I'm in the compound iron 2 chlorate. I would like to convert to iron 2 hydroxide. Luckily, that is a 1-to-1 mole ratio. All right, so I'm going to set that up right here. So for every 1 mole of iron chlorate, it's going to produce 1 mole of iron hydroxide. So easy step, it's just 1 to 1, but that's going to get me out of the reactant, and now I'm in iron hydroxide. So I actually already solved the problem. I know how much iron hydroxide, or I know how much precipitate's being produced. I just unfortunately just don't know it in the right unit. So the third and final step of stoichiometry is just convert to the unit it wants. It doesn't want moles of iron hydroxide, it wants grams. So anytime you're going from moles to grams or grams to moles, you use your molar mass. So 1 mole of iron hydroxide is going to have a molar mass of, and I'm calculating that right now, alright, looks like about 89.87. 89.87 grams is the molar mass. Okay, so that's FeOH2. Alright, so that gets me out of moles. And now I'm into grams, and that's what I want. So let's go ahead and calculate out what that would be. So 52.81 times 0.3189 times 89.87, and then divided by 1,000. All right, and if I do that, if I did that correctly, with significant figures, should be 4 sig figs, my answer, and I'm going to go ahead and write that here in blue, my answer should be 1.514. 1.514 grams. So that's if I used up all of the first reactant, okay? So I have to do the same steps now, or same stoichiometry steps for the second reactant. So now I'm going to look solely at this amount of sodium hydroxide, and I'm going to figure out if I use up all of that, how much iron 2 hydroxide will I create. So this first step is going to look a little different because now I'm starting out in grams. So my first step of stoichiometry, take what it's giving you, 0.4820, convert it to moles. So since it's a solid, I'm going to actually use molar mass, okay, grams to moles. So for every 1 mole of sodium hydroxide, it's going to have a molar mass. Actually, it comes out pretty much to be about 40. It's 40.00. That's a little squish, but that's 0.00 right there. It's like 39.999. So rounding it to 4 sig figs, it's 40. So that's going to get me very simply in just one conversion. That right there gets me into moles. So now my second step, let's use the mole ratio. So for every 2 moles of sodium hydroxide, 2 moles of sodium hydroxide, it's going to create 1 mole of the precipitate iron 2 hydroxide. Okay, so that gets me out of my second reactant, and now I'm in iron 2 hydroxide. The last step is now going to be the exact same because we already have it worked out up here. So for every 1 mole of the iron hydroxide, it's going to have a mass of 89.87. Okay, so let's do the math there and see what my answer would be. So 0.4820 times 89.87 divided by 40 and divided by 2. And so I end up getting, if I were to calculate this, or if I were to react all of my second reactant, the maximum amount of product I can make is 0.5415 grams. So now that we have those two, okay, now we take a look. If you reacted all of the first reactant, used it all up, you're going to make a maximum amount of precipitate of 1.5 grams. If you use up all of the second reactant, you can only make 0.54. So this is what's limiting us. So this first amount is actually not going to get created. So our limiting reactant ends up being the sodium hydroxide. And so the quantity you will put on the exam that gets actually created is 0.5415 grams. Make sure that when you get to this step, you need to cross this one out. if you put both of these numbers and you don't distinguish that this actually is the amount that gets created, you're going to get some points marked off because you need to make the distinction of saying to me that the 1.514 grams is not realistic. It's not going to happen. Stop trying to make 1.5 happen. It's 0.5415 grams. That's all you can make. All right, so that is the answer there, 0.5415. So then right down here, this last follow-up question, it says, based on your previous answer, calculate the percent yield if 0.4972 grams of precipitate are actually formed. So what that means is, theoretically, if everything went to plan in the lab and you didn't make any mistakes, you should have created this quantity, the 0.54 grams. But you didn't. You only created 0.49 grams. So you produce less than what actually was there. So that's what a percent yield is. It's wanting to figure out what is the amount that you created. So remember, percent yield is actual divided by theoretical times 100. Okay, so actually you got 0.4972. Theoretically, you should have gotten the 0.5415. And so then multiplying that by 100, that'll get us your percent yield. Remember, percentages also do have significant figures. Both of these numbers that we're using have 4 significant figures in them. So my percent yield will also have 4 significant figures. And my answer there is 91.82%. Not too bad. Remember, anything within 5%, so 95% or higher, is accurate. So this isn't as accurate as we would like it to be, but definitely not terrible. But we would like to see that higher. All right, so that is, like I said, probably one of the bigger questions you'll have on exam 3. So make sure you study how to do this question. All right, question 7, 2 parts here. First question is asking us to write a balanced molecular equation for the reaction of sulfuric acid with potassium hydroxide. So not only am I testing you to see can you write a chemical equation, but can you write formulas and predict products? So my 2 reactants are sulfuric acid and potassium hydroxide. Okay, so sulfuric acid is H2SO4. Remember to put aqueous, not only because it's an acid, but because anytime you have a double replacement reaction, or specifically in this case it's an acid-base neutralization, it's all aqueous. Okay, so make sure that you have that there. So that's sulfuric acid. Potassium hydroxide. Potassium is K, hydroxide is OH, but positive 1, negative 1, so it's written correctly, and then we just put the AQ. For my products, we're going to flip the hydrogen and the potassium. We're going to switch those spots. So potassium is going to bond to the sulfate, so KSO4. Potassium is +1. Sulfate is -2, so we need to put a 2 there. This is going to be aqueous. Because it's taken care of in an aqueous solution. Also potassium there, so that's definitely aqueous. And then the second product is water. Remember, anytime you have an acid-base neutralization reaction, the second product will be water. We just need to make sure that it is balanced out correctly. So it looks like we need a 2 right there to balance out the potassiums, and then a 2 here to balance out the number of hydrogens as well as oxygens. So then part B is going to build off of that. Part B, what volume of 0.448 molar sulfuric acid is needed to neutralize 23.0 milliliters of 0.406 molar solution of the potassium hydroxide? So first things first, a lot of students, for whatever reason, are tempted to do M1 times V1 equals M2 times V2. No, 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 no. Okay, never do that. That is what you use if you're diluting something. Okay, so only in dilution problems where you're just adding water to change the concentration is when you do that. This is actually a titration. So with titrations, you legitimately are using stoichiometry. So we're going to build off of this reaction that we have up here. Okay, so I'm going to go ahead and write the information that that problem just gave to me underneath the acid and the base. So it says what volume of the acid, so that's what I'm solving for, how many milliliters, but I do know its molarity, it's 0.448. The base, there was 23 milliliters, and its molarity was 0.406. So basically the question is saying how much of the acid is needed to fully neutralize with the base. So remember, always start out with the amount that you know more information of. So in this case, we know more about the base than we do the acid. And we're going to start out not with the molarity, because the molarity is just a conversion factor. We're going to start out with the actual volume. All right, so I'm going to start out with 23.0 milliliters of the base, which is KOH. All right, first step of stoichiometry, convert what you're given into moles. We are looking at a solution that is aqueous, so you're going to use molarity. So the first thing we need to do is we need to convert that to liters. So there's 1,000 milliliters for every 1 liter. Okay, milliliters is going to cancel out. And now we can use our molarity. So for every 1 liter of the base, it will contain 0.406 moles of KOH. So that's the first step of stoichiometry, convert to moles. So my liters is gone. Next step, use your mole ratio. So for every 2 moles of the potassium hydroxide, because of the 2 that's right here, 1 mole of the acid, 1 mole of the H2SO4 is needed because of that 1 that's right in front of there. So now we're out of KOH and we are now in moles of the acid. Now, since we know the molarity for the acid and we are going to figure out the number of milliliters, we can actually keep going with the third step. So down here, okay, we will go ahead and put, there is going to be 0.448 moles for every 1 liter of solution, because this right here is the molarity. We know the molarity for the acid. So if you know the molarity for the acid, you can use that as you can keep going with your stoichiometry. The moles will cancel out, and now I'm in liters. The last step, and hopefully I don't run out of space here, is to convert from liters into milliliters. And we just do that by multiplying by 1,000. So that'll get rid of my liters there, and now I'm in milliliters. Okay, so now we just have to calculate through. So 23.0 times 0.406 times 1,000 divided by 1,000. So those steps could have been canceled out if you wanted to. Divided by 2, and then divided by 0.448. Looks like we need to have 3 significant figures here. So my answer is 10.4 milliliters of H2SO4 is needed. There we go. So that's the quantity of acid I would need if I wanted to fully neutralize. Okay, so we're doing really well with time. We're on question 8 now. Okay, remember there's 12 total. So for this one, it says for each set of reactants below, you're going to do 3 things. Number 1, you're going to predict what type of reaction it is. It says using the choices listed in number 17. This was copied and pasted from a practice exam, so that's what it's referring to. So we're gonna write down the abbreviations for the types of reaction it is. If it does not have a reaction, we will write NR so that there's no reaction, so we know that. The second thing is, once we know the type of reaction, we're going to go and predict the products. And then finally, we're going to balance. Okay, so let's look at letter A. So first of all, we have magnesium reacting with copper nitrate, copper 3 nitrate. So I noticed that there is an element reacting with a compound. That's a single replacement reaction. But before I write single replacement, I notice that this is a cationic single replacement reaction. In other words, it's the metals that would be doing the switching. So remember, anytime it's a single replacement reaction and it's metals switching, you need to look at the activity series. So remember, on the back of your periodic table, on the right-hand side is the activity series. If this reaction is going to happen, the magnesium has to be more reactive or higher on the activity series than copper, and specifically copper 3+, but just copper in general. Okay, so if I look at the back of my periodic table, magnesium is pretty darn high on the activity series. It's if you look halfway and then go higher, not manganese, but magnesium. And then down below is copper. Okay, so this definitely is going to take place. And so the type of reaction, I'm going to put an SR for single replacement. Okay, those abbreviations will be provided to you on the exam, but for right now, just know SR is single replacement. Okay, next I need to predict the product. So the magnesium and the copper are going to switch spots. So the copper is now going to be the element that's by itself. And since it's getting displaced as the element by itself, it's now in the solid form, just like magnesium was when it was by itself. However, magnesium is bonded to nitrate. The charge for magnesium is positive 2, nitrate's negative 1, so we're going to need 2 nitrates. There we go. And then the state of matter for that is going to be aqueous, because remember, if it's aqueous on this side, you still have a solution on this side. Okay, so this is a single replacement reaction. We had our metal switch. The last thing we need to do is we just need to make sure that it's balanced. Notice you have 2 nitrates on the product side, 3 nitrates on the reactant side. There's that 3-2 ratio. So remember, we're looking for our least common multiple of 6. So I automatically know I'm going to have to put a 3 here to make the nitrate 6, and then I'm going to put a 2 here to make the nitrate 6. That means 2 coppers, and 3 magnesiums, 3 magnesiums. So that's how I would do that problem there. All right, the second question, or second part, letter B. All right, we have C3H8 reacting with oxygen. It looks like it's a single replacement reaction because you have a compound reacting with an element, but this is a specific type of reaction. This is a combustion reaction. It's a carbon-based compound that is reacting with oxygen. Sometimes we might say it's burning in air, or it's burning, or it's just combusting. So if I don't actually give you O2, but just say that a compound combusts, know that oxygen is the second reactant. But nevertheless, the reaction type is combustion. The abbreviation we use for combustion is the letter B. The reason why we don't use C is because C is reserved for a combination reaction. So we use B for combustion. Once again, I will provide you with those so you don't have to worry about remembering that. Okay, the nice thing about combustion reactions is you will always know the products. The products of a combustion reaction are always CO2, which is carbon dioxide, and that's in the gas form, plus water. Water is the second one. And water is the liquid phase. Some books will have water in the gas phase. Technically, that is more correct because when you combust something, the water is immediately turned into steam, but then it quickly condenses. So you might see water written as liquid, or you might see water written as gas. I accept both, so you can do whichever one you want. Okay, now we just have to balance these out. So we have 3 carbons, so I'm going to put 3 carbons. We have 8 hydrogens, so I'm going to put a 4 here to make 8 hydrogens. We have 2 oxygens, and then on the product side, we have 3 times 2 is 6, plus 4 times 1 is 4, so we have 10 oxygens total on the product side. So I need to put a 5 here to make that balance out to be 10. You don't have to put a 1 here since there's numbers here, but if it makes you feel better to put a 1 there, then that's fine. All right, and then the last one. We've got solid magnesium reacting with chlorine gas. These are 2 elements. So if they're 2 elements, they're going to have to combine together to make one product. And so this is going to be a combination reaction. So if they're combining together, we're just going to write Mg bonded to Cl. Make sure that you write them correctly. Magnesium is positive 2. Chlorine is negative 1. So we do need 2 chlorines. It's 2 chlorines not because it was 2 chlorines over here, but because it's bonded to magnesium, and magnesium is plus 2. For the state of matter, what would the state of matter be? Well, you have a solid and a gas reacting together. Whenever you have a solid and a gas reacting together, the simplest way to remember is that it will create a solid. That's just a pattern. So if you had solid, gas, it'll create a solid there. That was in one of your labs, actually. So that's how you'll know how to predict those states of matter there. As far as balancing it goes, it's already balanced. Now in this case, since it's already balanced, I'm actually going to write 1s, so that way I know that, like, if I read that you put 1s, then you're indicating that it is already balanced. If you leave it blank, I may assume that maybe you skipped it and you didn't balance it. So that's the only time I would really want you to fill in the 1s, is if all of them are 1s. That just tells me that it's already balanced. All right, and so that's how you do that problem. Okay, question 9. Identify what is oxidized and reduce. Also, identify the oxidizing agent and the reducing agent. So we're looking at redox reactions. So remember, to identify what's oxidized and reduced, you need to know what the oxidation numbers are for all the elements that are involved in the problem. So we're going to go through real quick, and we are going to assign oxidation numbers or oxidation states to each element. And remember, that's just another way of saying the charge. Alright, so Cl2, since it's by itself, it's not bonded to anything. Remember, an uncombined or unbonded atom, even diatomics, are going to be 0. Okay, now sodium bromide. I'm going to ignore the 2. You don't have to worry about the coefficients. They don't matter. So sodium and bromine, we don't know a rule. Actually, no, that's not true. We actually do know a rule for sodium. Remember, any group 1 element gets to keep its own charge. So sodium is going to be +1, and so then that means bromine has to be -1. And that makes sense because bromine's a halogen, and halogens normally are -1. Alright, on the product side, same thing. Sodium's got to be +1 because it gets to keep its charge. That means chlorine is -1. And then bromine right here is going to be 0 because it's an unbonded element. Now that we have that, we can now figure out what is oxidized and what is reduced. So the elements that is oxidized is the one whose charge went up. Okay, so we have chlorine went from 0 to -1. Sodium went from +1 to +1. Bromine went from -1 to 0. So the one whose charge went up is actually bromine. Bromine went from -1 to 0. It became more positive, so its charge is going up. Chlorine went from 0 down to -1. So whatever is reduced is the one whose charge went down. So that's chlorine. So notice, I don't have to write it Br2 or Cl2 because I'm just identifying what element is actually being oxidized or reduced. Now, when you are asked to identify what's the oxidizing agent and what is the reducing agent, you're just going to flip them. So whatever is oxidized is the reducing agent. So if bromine was oxidized, it is now the reducing agent. But you have to make sure you write bromine how it came as a reactant. So bromine didn't just come by itself. It came in the form of NaBr. So that's what I need to write, NaBr. Whatever was reduced is the oxidizing agent. So chlorine was reduced, so that's the oxidizing agent. You have to write chlorine how it came as a reactant. It came as Cl2. So notice the agents, the oxidizing agent and the reducing agent is where you need to be very careful. You write it how it is specifically as a reactant. The oxidized and reduced species, you just have to identify what element it is, and that's it. Okay, question 10. If you have 25.35 milliliters of a 0.450 molar solution of sodium carbonate, how many grams of sodium carbonate are present? And to help you out, I give you the molar mass. Okay, so this is not a stoichiometry problem, it's nothing like that. We're just simply looking at a solution that we know the molarity for, and we know the volume for. So remember, molarity, it can also be used as a formula or an equation. So molarity is equal to moles over liters. So molarity is the strength or concentration. Liters is how much you have in volume of the solution. Moles is how much you have of the solute. So in this problem, we know what the molarity is. It's 0.450. That's equal to, we know the volume of the solution. It's 25.35 milliliters, but we just need to change that to liters. So I'm going to move this decimal 1, 2, 3 places to the left. Okay, so the volume is 0.02535. And so we can actually solve for the numerator, which would tell us our number of moles. So what I'm going to do, just to show my math here, I'm going to multiply both sides by 0.02535. So that'll cancel it out there. And I'll do the same thing on this side. Alright, and so if we do that, that's going to give me my number of moles. So let me do that right now. 0.02535 times 0.450. I end up getting, I'm going to write it down here, 0.0114075, I'm just writing the whole thing, moles of sodium carbonate, Na2CO3, because sodium carbonate's the solute. I don't want to know moles. The problem's asking how many grams. So at this point, you just do a molar conversion. Okay, so 1 mole of sodium carbonate is going to have a mass of 105.99 grams, because I provide that for you right there. So by multiplying those, the moles will cancel out, and I will end up getting my number of grams. So this is my final answer. So significant figures, it looks like I have 3 significant figures because of the molarity. And so my answer is 1.21 grams of sodium carbonate. All right, so that one was very straightforward. Okay, 2 more questions. Question 11. This one's pictorial, so a visual one. A reaction takes place between A atoms and B2 molecules. That's shown here. A atoms are here, B molecules are here. What is the limiting reactant? Write the balanced chemical equation for this reaction. Okay, so notice what you have as products. So you made something new, whatever that is, okay, AB2, but then you've got B2 molecules left over, right? So let me do this. I'm going to take my pen here, and I'm going to write below. So we have, this is A, and we have 5 of them, plus this is B2, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, it makes AB2, and there's 5 of them. Okay, 1, 2, 3, 4, 5, and then plus 1, 2, 3, 4, 5 B2s. So first thing is, what's the limiting reactant? Well, this is the limiting reactant, the A atoms, because there weren't any A atoms left over. There were B2 molecules here, and so that's why B2 is the excess reactant. Now be careful, don't write this as the chemical equation, okay? Because notice you have 5B2, excuse me, you have B2 on both sides, right? That can be, it can be further reduced, right? Because did it actually take 10 B2 molecules to fully react with these 5A atoms? No. Of these 10, it only needed 5 of them because you ended up having 5 left over. So we're going to simplify this chemical equation. We're going to, it's called, you're basically algebraically simplifying or canceling out what you don't need. So I'm going to get rid of these 5 over here, and instead of writing 10 here, I'm going to write 5 because that's all you needed. So that simplifies now to be 5A plus 5B2 is all it takes to create the product 5AB2, right? Because we don't want to include leftover. So that looks pretty good. The only thing is, why do we have all coefficients of 5, right? Is that the simplest way we can show this? No. We can actually reduce that. So I'm going to go ahead and reduce that by writing out A plus B2 yields AB2. That is the balanced chemical equation for this reaction. Because remember, what does a chemical equation do? It tells you the simplest whole number ratio for the coefficients, everything's reduced, of what reactants are needed to make the product. So the product, it doesn't matter that there's 5 of them. The product is AB2. What needs to create AB2? You need an A atom, and for every 1 A atom that you have, you need a B2 molecule. So that's what a chemical equation does. It shows you that simple step, or that simple setup of what needs to be reacted to create your product. So that's how we got A plus B2 yields AB2 from this up here. So that was more of just like a visual problem there. And last but not least, question 12. It says identify the acid, base, conjugate acid, and conjugate base in the following. So remember that you have to go back to the definitions of a Bronsted acid and a Bronsted base. So a Bronsted acid, I'm going to write this down. A Bronsted acid is defined as a hydrogen donor. Okay, so it's going to give up its hydrogen. A Bronsted base is going to be classified as a hydrogen acceptor. So what you have to do to be able to identify what is the acid and base is you need to look at the reactant side compared to the product side and see where did the hydrogen go? Like what had the hydrogen and where did it go? So if I take a look at reactant side compared to product side, it would appear that this hydrogen went to the cyanide ion. And so that's why now you have HCOO without the H there, and now H has bonded to Cn. Notice also the change in charge. This compound was neutral until it lost the positive hydrogen. That's why it's now negative. This cyanide ion was negative until it gained a positive hydrogen, and now it's neutral. But that aside, that's what's happening. So because this compound right here donated its hydrogen, it is classified as the acid. Over here then, the cyanide is acting as the base. So now, over here are where you have your conjugates. So the product side is where the conjugates are. Remember, whatever was a base becomes the conjugate acid, and whatever was the acid becomes the conjugate base. Another way of looking at it is just find that hydrogen. Here's the hydrogen that moved, right? It's right here. It could easily go right back to where it came from, right? So that means since this compound now is in the position to donate a hydrogen, it is considered the conjugate acid. And this is in the position to accept the hydrogen back. So it is classified as the conjugate base. And just to kind of wrap it up, these two are known as conjugate acid-base pairs, and these two are known as conjugate acid-base pairs. Just so you would know that terminology. But that's all you have to do, is you just have to identify what's the acid and the base, what's the conjugate acid, and what's the conjugate base. So that review, or that concludes the review session. So you are more than welcome to email me if you have any questions on any of this. For those that were in the review session with Canvas, I do apologize for all the technical glitches. Hopefully this video made up for that. And like I said, any questions you have, please reach out to me, and I will see you all this weekend.